Now, the American Gunsmithing Institute presents another instructional video on firearms design, operation, maintenance, and repair.
Hi, I'm Fred Zeglin. I'll be your instructor for the AGI course on Taming Wildcats. In this course, we're going to go through everything you need to know about wildcatting cartridges. If you're a novice, we'll be able to take you from the beginning steps all the way up through the most advanced things that a wildcatter can do. If you're an experienced wildcatter and have done this sort of thing before, you're going to learn things that you probably hadn't thought about before. There's all kinds of simple little techniques and cute tools that amazing things to simplify the process and help you to become a better wildcatter, better reloader. Now, prerequisites. It's important that you know how to run a lathe. It's not absolutely essential, but it's a very good idea if you know how to run a mill. And it is very essential that you have a pretty good working knowledge of reloading as just a general practice. We're going to talk a little bit about the history of wildcatting. The simple parts of it are that, most people ask, where did wildcatting come from? It really started when the first metallic cartridges became available. People immediately started trying different things and reshaping cartridges to get an improvement, to try and get something that would be better than what was available from the factory. So it was almost immediate. If you look back to the early 1900s, late 1800s, people were already trying this. Whoever established the word wildcat in connection with this process is really unknown. Wildcatting became not only a hobby, but for many gunsmiths, almost a business. Some of the earliest names in wildcatting are Donaldson, Gebbe. Charles Newton was a man who was pretty amazing at the turn of the century, far ahead of his time. He took some time to design some cartridges and then take them to some of the manufacturers and try and get them to pick them up. One of those was the .22 Savage High Power, which enjoyed popularity for many years. It started out its life as a hunting cartridge. In Charles Newton's eyes, it was supposed to be a deer class cartridge, and unfortunately the public doesn't always agree with the person who designs it. The public decided to use varmint type bullets in that cartridge because it was a .22, and ultimately what that caused was wounded animals, and the people who were in charge of game management at the time saw that as a problem. And in the magazines you would see arguments back and forth about whether a .22 was capable of performing the job of hunting deer, and ultimately it caused the demise of small cartridges like that in that time frame. Charles Newton went on to do many more cartridges. He started a company called Newton Arms, and at a later date it collapsed at one point and then was restarted again under another name. Newton had a number of cartridges, the 30 Newton, 35 Newton, and if you look in your reloading manuals, something like Cartridges of the World, you'll find a fair amount of history on Charles Newton and the cartridges he designed. Charles Newton was interested in high velocity and in a way that was far before his time. The powders that were available at that time simply could not produce the velocities that are required for the type of cartridges he designed. Ultimately, this combined with the fact that the rifles he designed for his cartridges were very lightweight, so they were high recoil, and the shooting public as a whole just did not accept the concept of high velocity and high recoil, which is not too surprising, I suppose, because nobody really loves to get punched. The next thing we wanted to talk about is some of the more current wildcatters or more recent wildcatters. The most famous, of course, of the last century is P.O. Ackley. Mr. Ackley spent most of his career in Salt Lake City. He developed a huge reputation strictly based on wildcat cartridges. He was also a barrel maker, which produced, it's where he made a lot of his money. But the whole idea of wildcatting gave him an anchor in the industry, made him an expert, and made him a go-to guy. What he did was, the ones that most people are aware of are the Ackley improved cartridges. And the difference between an improved cartridge and a Wildcat is a pretty important distinction. An Ackley improved cartridge or any other form of improved cartridge should be able to fire factory ammunition safely in order to form the brass. And a Wildcat cartridge, on the other hand, you're required some way to form the brass in dies or in some other method prior to being able to fire form them in the gun. P.O. Ackley's improved cartridges were an important step in the process of wildcatting in this country and of course worldwide now. If you look at his cartridges, you'll see that he did a huge number of them and in all different sizes and shapes in order to draw customers at all levels. Why that's important to us, there's a couple reasons. First of all, the improved cartridge is a simple cartridge that anybody could accomplish. You can take any new factory offering and figure out a way to improve it. And that simply means moving the shoulder forward or bumping the shoulder out, I should say, and expanding the body to increase the amount of case capacity. Again, the description of an improved cartridge means that it will fire factory ammunition safely. Now, when we talk about doing a full Wildcat, which is the point of this course, we're going to be forming brass through several steps. It will have to be either stepped up or down. It will have to be reformed with the shoulder moved to a different position. Headspace will be changed, and it's important to understand the concept of headspace and how that's going to affect the design that you create. And we will go through all of that in the process of doing this course. Now, the design process, as I call it, we've broken down into 5 simple steps. And the first, of course, would be your idea. You have to have some concept of what you want to build, a reason for building it, and so that's going to be the first thing you do. The second thing would be to do some research, find out what other cartridges are out there and how they're similar to yours or different from yours, and if you really are making something that's worth doing. The next thing would be to create a drawing. And when you create this drawing, the idea is to put down the dimensions in such a way that you will be able to physically compare it to the other existing cartridges on the market, and also to make sure that it will fit in the gun that you're working with. So the next step is actually comparing our cartridge from our drawing to the other available cartridges and the other possible Wildcats that are already out in the market. And once we've done that, we make a decision. Are we going to build this cartridge or not? Is it worth the effort? Is it going to give us something new and unique that's worthwhile? Sometimes the answer to that is as simple as the client wants it and he's willing to pay for it, so it's done. If you're doing something that you think is going to provide something new in the industry to cut some new ground, in that case you want to really carefully look at whether or not you're doing something new. Every class I teach on this, somebody designs a 308 Winchester or a 222 Remington mag or something like that, and that has to be pointed out to them. So research, I guess would be the best way to put it. You really need to think carefully about whether you're repeating history and whether what you're doing is really going to present something new. If it doesn't, then it's really not worth doing. Just designing a cartridge to put your name on it will eventually get boring and probably won't make you any money. And if you're in gunsmithing to make a living, then making money is important. So at that point, I would recommend that you make that decision based on just simple common sense. Is it going to give me something new, something worthwhile, or something valuable? So let's get started. I'm going to choose one particular Wildcat to carry you through this process, and we'll go through each and every step that's needed to design it and create it. However, that won't be the only thing we do. We will take side steps and look at other cartridges and other processes to make sure that whatever you decide to do, you'll have some information that will lead you down the correct path and allow you to finish this project yourself. We're not limiting you to the project we're doing. You can go any direction you need to. So let me get ready for the first step and we'll be right back. Okay, we're ready to start the idea. The idea is based on many different things. It could be you want to have a cartridge that will work in a specific gun that has, you have limitations with length or size in some way. Perhaps you're looking strictly for more powder, more velocity, more bullet weight. Other reasons for doing wildcatting like this would be to actually reduce case capacity and come up with a cartridge that's going slower. We're going to have a few examples here to show you to give you some idea of how that works. Generally speaking, people get into wildcatting because they're interested in different performance. They're looking for either more velocity or less velocity or some other change that fits the thing they're interested in. Another reason would be to have a cartridge that fits a specific firearm, whether it be for length reasons or size. There are a lot of reasons why you might have to tailor a cartridge to fit a particular action. However, there are some people who do this specifically for the challenge, and there's nothing wrong with that. I have a few samples here I'd like to show you, and we're going to talk about the reasons these cartridges came about and some of the performance that they achieved with them. This particular piece of brass is the 470 Imbogo. This was designed by a guy named Dave Estergaard, and his purpose in designing this cartridge was specifically so that he could go hunt Cape buffalo, and he wanted a cartridge that used a 470 bullet and as much case capacity as he could possibly put behind it. And one of the interesting things about this particular cartridge is he actually went to the expense of having head stamp brass made. And you can see that here that Quality Cartridge makes this brass. They're one of the companies that it's listed in your notes, and they are capable of making head stamp brass in small quantities, which is a very interesting aspect of wildcatting today. It's something that just a few years ago wasn't possible. Now we'll go on to the next one here. This particular cartridge is the 50 Dampf, and a gentleman by the name of Belden Dampf brought this to me wanting to have reloading dies made for it. It's a 460 Weatherby that has been cut down in length, and then he's using a 50 caliber bullet. The reason for this cartridge was in the state that he lives in, the Fish and Game Department needed a cartridge that would be subsonic, that they could use near communities to use in a silenced firearm, and they were taking elk that were too close to town and had population problems. So this was a solution for Fish and Game to be able to solve a problem and not have the little old ladies in tennis shoes upset with them for killing the elk. Okay. Another big one, this is a 450 Alaskan. Some of you might recognize this. It's a cartridge that was designed by Harold Johnson in Alaska in the 1950s, and it's a 348 Winchester case that has been blown out and necked up to 458. And the reason this is a popular cartridge even today is because it works in the Winchester 71 lever action. Those have been reintroduced as a Browning 71 in the last few years, and consequently there's been a lot of people building these guns so that they can take them to Alaska. I have a couple of clients who are professional guides in Alaska who have sent guns down and had them reworked into the 458 and even the 50 Alaskan, which is this same case necked up to 50 caliber. Now this next one is a cartridge that I'm pretty proud of. This is a 19 Hawk, and the 19 Hawk came about as a result of an article I was reading. I've been interested for a long time in wildcats, and so I've done a lot of research on the various cartridges that have been popular over the years. The 219 Donaldson Wasp for many years was popular on the bench rest circuit. The whole purpose of this cartridge was to develop the same general characteristics as the 219 Donaldson Wasp, yet use a 19 caliber bullet. And that combined the concept of the 19 caliber bullet, which had been tested in NATO testing several years ago, and it had proved in some cases to be superior to the 22 caliber bullet, although it lost the trials. So that was an interesting concept to me, to have a 19 caliber bullet for varmint purposes, and I started looking at what would be the possibilities. In fact, in my book I did a theoretical design of this cartridge as an example of how to design a cartridge. After the book was finished, I thought it was such an interesting idea that I went ahead and built it. Basically, this is a 7.62 by 39 case that we set the shoulder diameter right here at 400, and then the shoulder angle itself was set to match the same profile as the 219 Donaldson Wasp. The concept behind this cartridge was to retain the same case capacity, taking into account the fact that we have a reduced bore diameter, which is going to change your ballistics. So we were trying to duplicate the results you'll get with a 219 Donaldson Wasp, only in a 19 caliber case. I love the 19 Hawk. When my wife and I get ready to go out shooting, the first gun she reaches for is the 19. It's the particular gun we have is a very nice looking gun, so I think she likes that, but she loves the fact that it's low recoil. My favorite thing about this project is that it actually met all the criteria we had in mind when we started the project. It produced the ballistics, it produced the accuracy, and again, it's low recoil. So it's everything that I was looking for in a new varmint cartridge. It doesn't bother me that there's only one manufacturer of bullets. And sometimes you'll get this argument from clients that hey, there's only one or two sources for something. I always tell them just to figure out how much are you going to shoot this over the course of the life of the gun or over your hunting lifetime, and divide that up. And you can buy, 500 rounds of brass, or you can buy 2,000 bullets, and you have covered the number of components you're going to need for the life of that gun. And it's usually not as much money as people think, and it's really not as difficult as people think to have that supply of material on hand. Now, I want to talk about when you have an idea and you carry it a little too far. My concern here was I had read an article by a guy he described the cartridge he was talking about as a circus midget on a shot of lemon extract. And I thought, well, the cartridge he picked wasn't all that interesting to me, but the whole concept of a circus midget in a cartridge I just thought was interesting, and I thought it'd be interesting to see what I could build that would fit that description. This is a 348 Winchester case, neck down to 17 caliber. Now, it's a great example of what you should not do. In order to accomplish this, it took a huge number of dies, because you're taking a cartridge that's over 2 inches long and pushing it down to, I believe this is 700 thousandths in length. The disadvantage is the closer you get down into this area, the heavier the brass is, and naturally it's not going to form very well. And I have one here that's sectioned. Let's see if we can stand it up so you can see it okay. And you can see just how thick the brass is, especially right in the shoulder area and whatnot. The more thickness you gain here, the harder it is for that brass to make the turn in the die and become a good, clean, sharp shoulder. And so that's a consideration you want to keep in mind. This is too much brass in the neck area and in the shoulder area. You're going to have problems with pressure, you're going to have problems with neck tension, accuracy will be a problem with a cartridge like this. And of course this was just for fun to see if it could be done. And we proved that yes, you could form the brass and get there. In order to actually seat the bullet in this cartridge, we had to do some neck turning and thin out the brass in order to get that in there. But again, this isn't even a cartridge that we've built a gun for. This is a cartridge that we just did as an exercise to see if the brass could be moved and what would be accomplished when we were finished. I have no idea what the ballistics would be on this because we never got that far. But I wanted to show you when the brass is too thick, it creates all kinds of problems. Okay, we've taken you from one end of the spectrum to the other on these cartridges and how they can be shaped and formed. Now let's take you to an example we can use in this course to go through the design process and show you all those steps in a logical form. This particular cartridge I called the 358 Indy. And the reason this cartridge came about is mainly because clients were contacting me from the state of Indiana wanting to know if we could build a cartridge that would fit the specific rules they have. They recently had a regulation change where they're allowed to use rifles. It's always been a shotgun-only state. And this cartridge fits those standards. They were required to have a cartridge of 357 or larger in diameter, and it had to have a length of, I believe it's 1.61 to 1.625 in length. And the idea behind the regulation was to limit them to 357 maximum. Although the way the regulation was actually written, it didn't specify that cartridge, it didn't specify any particular cartridge at all, it just gave a length measurement and a diameter measurement. So this cartridge is a 25 WSSM, the super short magnum, necked up to 35 caliber, and there's really no other changes, but it is a little bit more complex than a simple necking job because we have to, in order to do this, we have to neck it up larger in diameter and then turn the necks in order to get the brass the correct thickness and then size it back down. So it gives us a number of steps to look at in our process of understanding how to wildcat. Keep in mind this cartridge doesn't exist yet. We just gave you a small glimpse into the future so that you'd know what direction we're headed in. The very next step is for us to start our research. The research's purpose is to allow you to find the brass and the actions that are appropriate to this project. All right, let's talk about research. I use a lot of different methods to do my research, a lot of different books. I also use some computer software. I'll show you some of that here in a little bit. There are a number of good books out there. I always like to remind people that a friend of mine, his name's Phil Filing, says that a gunsmith without books is like a room without windows. And I think that's pretty descriptive. You know, gunsmiths tend to work in a small shop someplace and not get out a lot. So I highly recommend to you collect a large collection of books that are going to allow you to learn from other people's mistakes, to learn from other people's successes. You know, I'm a firm believer in standing on other people's shoulders. A lot of people have gone before me and made lots of mistakes. I don't have to reinvent the wheel, and neither do you. So when it comes to the books, there's a whole lot of good ones out there. The things you're looking for are information on cartridge dimensions. You're looking for information on pressure. SAMI in particular, that's our agency, if you want to call it that, in the United States, where the ammunition manufacturers have all agreed upon specifications. If you find SAMI standards, they're very useful. One of my favorite books is this Ammo and Ballistics by Bob Forker, and this happens to be the second edition. I understand the third edition is out now. The advantage to this book is that when you look at it, it contains a great deal of reloading data, but it also has a complete cartridge drawing, you know, and we have also a couple of different kinds of pressure data listed under specifications here. We have standard bullet weights, we have velocity in feet per second, and then we have copper crusher units and transducer units, which is PSI. The difference between copper crusher and transducer is just literally worlds apart. They are not directly correlated systems, meaning that you can't take the two of them side by side and match them up. Copper crusher is the older system, and it was based upon the concept that you can take a piece of copper of known size and known quality and crush it, and it'll give you, when it crushes, that dimension can help you measure pressure. Now it measures only the peak pressure because when it is smashed, it's going to go to that peak pressure and stop. So you don't get a linear progression, you do not get a form wave that you can read that tells you what the pressure wave looked like. So in that respect, it's fairly limited data. The other thing that we know about copper crushers is they're fairly limited in terms of quality and quantity. There are agencies that make this material for testing purposes, and they're very reliable. They've been doing it for a long time. But because we only get the peak pressure data, we're not getting a lot of useful information. Transducers are a little different. They're a simple device glued to the outside of the barrel, and the dimensions of the steel are entered into the software, and this allows the software to translate the stretch of the steel through the transducer into a waveform so that you can actually see in real time the form of pressure, so that it starts low, runs high, drops back down, and you can, with everything entered, you can even see the exit point of the bullet. That's very useful information, and if you stay with wildcatting for long, you might want one. There are a couple of companies that make them. We provided that information for you at the end of this disc. Also, there's many books that are useful in wildcatting. I use Cartridges of the World a great deal by Frank Barnes. It has a number of historical cartridges as well as current cartridges, so you're able to compare back and forth. It has a great deal of data that's just not found anywhere else. My next favorite probably is P.O. Ackley's Handbook for Reloaders and Shooters. He produced those about 40 years ago, but because they're a snapshot in history, they give you all kinds of data. Mostly it's pictures of the cartridges, so there's not a lot of data in terms of dimensions, but there's a lot of load data, there's a lot of descriptions of how things were designed, who was involved in it, so there's a lot of history there. So those are excellent books. A more current publication is Ken Howell's book, Designing and Forming Custom Cartridges. This has become kind of an industry standard. It has pretty much all standard cartridges in it, but it has a huge number of Wildcats, and there are very few errors. It's a very good quality book, and it's all dimensional information. There's no loading data in that book. There are a number of articles about how to form brass and various aspects of the reloading process and wildcatting. So it's a very good book for those of you who are interested in this subject. Another good book is Pet Loads by Ken Waters. That's really a collection of Ken's articles over the years. He's a man who spent more time at the range than probably anybody you'll ever meet, and so his data is real world. It's not something that he made up from computer software or something. He actually went out and shot every shot in the articles he writes. The Handloader's Manual of Cartridge Conversions by John Donnelly is also a very good book. It's primarily a dimensional book. It has different cartridges than in some of these others, so again it has value simply because it has different information. Wildcat Cartridges, Volumes 1 and 2 from Wolf Publishing, is a collection of articles from Handloader and Rifle Magazine that cover Wildcats. These articles stretch back to the early days of the magazine all the way up to present, and very valuable because they involve a lot of shooting, a lot of various situations that these cartridges were tested in, so there's a lot of information there that you wouldn't get anywhere else. Another really good book is Wildcat Cartridges by Richard Simmons, and this isn't the Richard Simmons of current fame. It's a guy who was really into guns in the mid-40s and 50s. Richard was very well known at the time, was a well-known writer, and what he did was he collected a huge number of cartridges, took photographs of all of them. They're all in this book, and he talked to virtually every well-known gunsmith of the day. So when you go through this book, it's broken down by gunsmith, and it has a collection of all of the cartridges done by each guy. And this is hugely helpful when it comes to trying to determine if you're repeating history, because you can actually look at these cartridges and see how they relate to what you're doing. My own book, Wildcat Cartridges, not a real clever name, but it's very descriptive, is a more modern book. It was published in 2005, so it has a combination of historical material as well as a whole section on current popular Wildcat cartridges. My attempt was to kind of draw a similar line with Ackley's book, the difference being that I gave dimensions for all my cartridges rather than photographs, although there are pictures of various parts of the process in the book. But the main thing there is that there is a huge amount of reloading data, description of each cartridge and its history, wherever possible, some of its lineage, how it came to be to begin with. Another very good book is Charles Newton, Father of High Velocity by Bruce Jennings. This book covers the history of Newton's design process, the different companies that he developed to try and market his ideas. Charles Newton was far ahead of his time. He, as I said earlier, he developed cartridges that really couldn't be brought to their full potential with the powders he had at the time. This is a man who designed cartridges and sold them to other companies, which is almost unheard of even today. The latter half of the book about Newton is made up of writings from debates between him and E.C. Crossman, which took place in the early part of the 1900s. Gives you a great perspective on the way his mind worked, how he defended his cartridges, and why they were better than the earlier designs. And it's just a really interesting view of a man's mind from the inside. The next book I wanted to mention was 22 Caliber Varmint Rifles by Charles Landis. This is a book that was written in the 40s, right after the war, and what was very popular at that time was varmint hunting and small calibers. People had the sense that we were encroaching on wild lands, and well, also the sense that a lot of the places where good varmint hunting took place was right on the edge of a city. So the tendency was to look for small cartridges with low report. So 22s became very popular, and that was kind of the reason that this book came about. He covers cartridges from just about every gunsmith who was working at that time, including P.O. Ackley, Jerry Gebbe, and just about anybody else, Donaldson, anybody you can think of. Very valuable in terms of varminting. If you're interested in small calibers, this is a book to read. Some Simplified Interior Ballistics by William C. Davis Jr. is a pretty easy read. It's a very current book, and it covers ballistics internally as well as externally. So it helps you to understand all of the things that are involved in what happens when you pull the trigger. And it's a very complicated subject. This particular writer tries very hard to make it understandable for just about anybody. Yet he's giving you enough information that you'll definitely learn something new. And the last one that I wanted to mention was Understanding Firearms Ballistics, 4th edition. This one's by Robert Rinker. It's a more basic type book. It's going to be a little easier to understand if you're somewhat of a novice. And he makes every effort to make a complicated subject understandable to anybody. And that's kind of it for the books. Now, that doesn't limit you to this list. There are lots of good books out there that are going to be valuable in your library. I would recommend that you collect as many different reloading manuals as you can. Each one is filled with not only reloading data, but specifications for cartridges. They also contain a great deal of information about powder and burning rates. There are a number of articles in every manual, and each one has something a little different. And you'd be surprised. Go to your shelf and pick up your favorite reloading manual. Open it up and look in the front. You're going to find there's a whole bunch of articles in there about various aspects of reloading and shooting in general. A lot of useful information. Each reloading manual is going to have different articles covering different aspects of the shooting and reloading hobby. So I would recommend that you go through and find out what you've already got. You probably have quite a bit. The next thing we'd like to look at is software, and I have a couple of pieces of software that I like to use. The first one is called AccuLoad, and AccuLoad is valuable for a couple of reasons. It has a very large database of cartridges, including dimensions, some information, usually a commentary about them, where they came from, who designed them. But probably one of the most valuable aspects of it is it has a archive of articles. The articles themselves are not there, but it tells you where this cartridge has been mentioned in print. So if you want to do more research, you have a simple and easy way to go find more articles about the particular cartridge you're looking at. So that's one of the main reasons I use that software. It also has a built-in calculator where I can take the case capacity of the cartridge and it will generate load data for a new Wildcat so that I can have a safe starting point and go start the process out at the range. Another piece of software that I use is called rcbs.load. It's valuable for a lot of reasons. It has a large collection of reloading manuals built into the software. They don't come with the program itself. They are an additional fee that you pay to the publisher. But the advantage to that, of course, is you can very quickly access information simply by clicking on a cartridge and telling it to upload that data. So it's very useful in terms of having a lot of loading data right at your fingertips. But one of the reasons that I use this software is because it has a built-in cartridge designer. The value of that is that you can take the parent cartridge and redraw it to your new Wildcat design. The software itself will take the corresponding data and adjust it for the new design. I'm going to show you how that works in just a minute on our project, but right now I have a couple of cartridges on the screen that are a comparison so that you can get an idea of what the software looks like when it's in use. On the left we have a 458 Winchester, and on the right we have a 458 2-inch American. Now the advantage to having a comparison side by side like this is you can take a look up in the corner here. We have some specific data for the cartridge in question. Initially it tells you what the cartridge is, or if you had a Wildcat name it would be listed here, and then it would list a parent cartridge. Case capacity in grains of water is very important. This isn't case capacity in powder, it's in water. The way that is measured for this system and virtually every other that I'm aware of is to the top of the case mouth. When you do water capacity in a case, if you do it below the mouth of the case, you're going to get an inconsistent number. Some cartridges don't have a neck at all, so there would be no way to be uniform. So to be uniform, be sure you do your water weight capacity right to the top of the case mouth. The diagram includes dimensions for the diameter of the case, and on the right you're going to have length dimensions. As you move up the case, you'll get a length dimension for the full length as well as a mouth dimension here. This is your diameter of your mouth. And then it'll also give you an overall length. This is assuming the overall length for a magazine. This is a maximum length. So you can see why the software is so valuable to us when we do our research. The research is the most important step, I believe, in the process. I said before, research, research, research. I really believe that. If you spend time reading about cartridges, if you do the research in books, use the software, it's very valuable. It's going to make it easier for you to make these decisions as you go down the road and not waste a lot of time on things that just won't work. So I wholeheartedly recommend to you that you get a bunch of books, read them, research, look at the differences between cartridges and try and get a feel for what would be an interesting transition from a big cartridge to a small cartridge, or more velocity. How am I going to get that? Oh, okay, I need more case capacity. The more you look at these things and spend time looking at case designs, the more interesting it'll become to you, the more exciting it'll become, and it's just plain fun. Now, I think we should probably move on at this point and talk about our project that we were going to get into with our little 358 Indy. And I think in order to do that, we should probably just go to the software. That'd be a good place to start. Okay, so here you can see the index of cartridges that's within the cartridge designer in rcbs.load. It ranges in cartridge size from as small as 14 caliber up to stuff as big as the 577 Tyrannosaur, 585 Naiadi. So a pretty good range of cartridges. A lot of Wildcats are included, so let's kind of look through it a little bit and work our way across looking for a cartridge that's going to work good with our project that we're working on. Right now it's on 14 222 Walker, and it's as simple as just moving to the cartridge you want. And as you move across, it's going to jump from column to column. Here's another Wildcat, the 220 Watkins Wilson Arrow. And we'll just keep moving across. We're going to look for a 35 caliber cartridge that we think would be appropriate for what we're doing. So if you have a little bit of knowledge about the kind of cartridge you're using and what you're wanting to accomplish, you can kind of go to something. Now we know we want a 35 caliber. Let's start with a cartridge in that classification and see what happens. So we're going to go to the menu here and tell it to draw this cartridge. We're on the 358 Winchester right now, and it draws the cartridge for us with all the dimensions so that we can kind of make a determination as to whether this is something we want to use. Now the first thing you're going to want to think about is the diameter of the case. Is it big enough? We know it is because it's already a 358 caliber. So the next thing we're interested in is whether or not we have enough shoulder diameter and length, and we clearly do because it is a 35. The big consideration here is going to be, do we have enough case capacity for what we're trying to accomplish? In order to make this cartridge work, we would have to adjust the length considerably. Right now it is a 2.015 in length, and we would have to shorten it almost 400 thousandths. The midpoint of the shoulder is about where we'd end up for our overall length. Consequently, we would lose a lot of case capacity. Now, that doesn't mean it wouldn't work. I think this cartridge would meet our needs. It would. We can shorten it enough. We'd still have a shoulder. We'd have everything we need to make a functional cartridge. So this is one possibility. But I think we should look at some others. Now, what I'm going to do is I'm going to go to, we can leave this cartridge up for reference. We can go back to the reference menu and choose another cartridge. A lot of people, when they start working with Wildcats, like to work with single shots because it gives them an opportunity to build an inexpensive gun and test a new idea. So one of the things we might try here is to look at a rimmed cartridge to see if that would work for our project. So we're going to just move across and find the 35 calibers again, just a simple way to do it. I happen to know that a 357 Harriet is close to our specifications for length, so we're going to go there. We'll click Draw. We now have both cartridges on the screen at the same time. So we have the 357 Harriet on your left. When we look at the overall length, it's clearly long enough for what we're trying to accomplish. The shoulder position is far enough down so that we could shorten the neck and have a cartridge that would fall within our length parameters. So this cartridge too would work. So either one of these cases would work just fine, but there's another consideration. We need to think about performance. Deer hunters are going to be looking for something that will allow them to have a little more power. These two cases may or may not be what we want. Let's look up the 358 Winchester and see where it falls in our power range. And I want you to get the idea of going back to another book. You're not limited to the software, you're not limited to one book. Do research, move back and forth between the different pieces of material that you have at your hands. According to this book, the 358 Winchester is going to have about 2,370 feet per second for velocity, which is pretty minimal for a deer class cartridge. So if we shorten that case and minimize the amount of powder we have in it, we're going to have a case that is really not much of an advantage over the pistol cartridges that are available in that range. And because the 357 Harriet is even smaller yet, we know that we would also be limiting ourselves to a fairly low power cartridge. So we're ready to go back to the directory and look for some larger cartridges, something with more volume. Before we do that, we should write down the case capacity of the 358 Winchester so that we have a reference point. We know we need something that will at least be this large. So we're going to go back to the software. I'm going to make it a large screen so we're only looking at one cartridge. So we're going to move to the upper left-hand corner of the display. You'll note at the top that the name of the cartridge is listed. The next thing down is case capacity in water, in grains of water. But that's not the capacity of the 358 Winchester. It's a theoretical number that you can use for design decisions. And you'll notice that down below that there are a few more numbers giving different tapers. Again, these are theoretical numbers to help you make decisions. The number without the neck is, again, another thing to help you make decisions. In order to get the information we need on our cartridge, we go down to bullet seating depth, and we right-click on that, which selects that item. Now we're going to jump to the other side of the screen, and we use these little arrows to change the dimensions on this particular cartridge. So we're going to go up 1,000th, just one click. What that does is it confuses the software into believing that we have seated a bullet 1,000th into the neck, so it's going to give us the full case capacity of the cartridge. So now we'll go back to the other side of the screen. The first thing we'll notice is the bullet seating depth has been changed to 1,000th. And then a new line has been added. We come up and look, and it says with bullet, and it gives us a case capacity of 58.7 grains. So that's the number we're going to write down as our full case capacity. And that's for the 358 Winchester. It's important that you keep track of these little details so that as you progress along, you'll be able to match things up. So now let's look at the cartridge drawing again. We want to collect a couple of other pieces of information. We want the shoulder diameter, which is 454, and the base diameter, which is on this drawing is 4709. We can just call it 470 and that'd be close enough. So we're going to write that down, base of 470 and shoulder of 454. We're going to use that information later to make sure that we're looking at a bigger cartridge. So we'll close this particular pane and we'll go back to the reference library and pull up another drawing. And it's my idea that we'd go to a Magnum case to see if we can get something that's bigger. So we'll go to the 358 STA, that happens to be a large Magnum, draw it. Now the 358 STA is plenty long enough, so that's not a concern. Now let's look at the shoulder diameter. It's 495, so we're very large there, and at the base we're 0.513, so we're quite a bit bigger than we were with the other cartridge. Now, one of the disadvantages to going to a belted case is when we do a short design like we're talking about, that could present feeding problems because a belt is just one more thing that has to be fed through the system. So while it's a great way to headspace and you know, a lot of people believe adds strength to the case, there is the disadvantage with feeding, especially in a stubby case. So we may not want to choose this cartridge just simply because of the added difficulties we might get from this belt. In addition, let's look at the shoulder. The shoulder height on this case is 2.486, which is very long, much longer than we need for our cartridge. The concern that you'd have there is when you go to reform this case, you'd have to push this shoulder down far enough on the case to leave you an appropriate length neck, and also to provide a cartridge that fits our parameters. So it'd be a lot of work. We'd be moving a lot of brass, and it would take extra tools. So not the most efficient use of our time, and that might not make this the best choice. But we can put it on our list because it would work. So we'll just write down the 358 STA as a possibility. And then we can go back to the directory and look for something else. So we'll close this pane, go back to reference, and some other big magnum. I know that there's a non-belted magnum, like a 300 Remington Ultra Mag would be a good choice. So let's see if we can find it here. Remington Ultra Mag. And then we'll just tell it to draw. Okay. Now, this case is 2.85 in overall length, so it's plenty long enough. Again, the shoulder is very high. It's 2.544. And base diameter is 550, so it's larger in diameter. That's a big advantage for us. We're going to get a lot more case capacity from a larger diameter case. We know that our 358 was 470 at the base from our notes, so this would give us quite a bit more case capacity. Again, this one has the disadvantage of we would have to shorten it considerably, and a lot of these cases, when you shorten them a great deal, are thick in the case wall, especially right here in the midsection of the body. So it's a good idea to avoid that kind of change in the brass if you can, because you're going to have to do some different reaming and thin out the brass in order to make it functional. So while this one has more case capacity, I probably wouldn't pick it because there's so much brass work that I'd have to do. So we'll close this pane and go on and look for another cartridge that might work. We'll go back to our reference chart. This time let's try something that we already know is pretty short. So I'm looking at my directory of cartridges here, and I see that the 25 Winchester Super Short Mag, or the WSSM, is not listed. And that might present a little bit of a problem, but I've told you before, and I can't say it often enough, you need to have other resources. So you could either go to a book, or in this case I'm going to go to another piece of software that I'm pretty sure will have what we need in it. So we're just going to close this window, and we will move on to that other piece of software and find out if we can do that. So bring up this software now. This is a little different look. On the left-hand column we have our list of cartridges, and we're going to look for the 25 WSSM, and all you do is tap the bar here and bring it down to find the higher calibers. And we're in the 25s, and now we've gotten to where we're starting to see dashes and various caliber designations, so we're past where it would be. I don't see a 25 WSSM. I did notice when we came into this that at the top there's a 223 WSSM, which is very similar to what we're looking at. So we'll go back to that cartridge and use it. And I know from personal knowledge that that cartridge is extremely close in dimensions to the cartridge we're looking for. So we can use it as an example, and it'll give us a good comparison. So we'll just go ahead and go to that cartridge, and it'll automatically fill in the data on the right hand side here. First we notice that the water weight capacity right here is 52.8 grains, so we'll write that down, and that compares very nicely with our 358 Winchester, which we looked at earlier. It was 58.7 grains. We decided that that cartridge was pretty much a minimum for what we're trying to accomplish. So we know that this cartridge, at least on case capacity, is pretty close. So let's see what we get when we look at the diagram. It'll show us the cartridge. Now what we have in the cartridge is, we'll look right here, is our overall length, 1.670. Now that's very close to our dimensions that we're going to have to use overall. The diameter of the base is 535, so it's much larger diameter than the 358 was, so we're going to have a greater case capacity. Now the problem you might notice is the neck diameter is pretty small, and that's going to skew our number for our water weight capacity a little bit. Now when we redraw the case at later in the program, you'll see that we can calculate what the actual water weight capacity is going to be, so that's not a big issue. We're just going to use this drawing clearly to tell us that this is a potential cartridge for our project. In the real world, I selected the 25 WSSM for this particular project, and the reason I did was related largely to the fact that it was very close to the design parameters. And that's one of the things we want to emphasize. The more cartridges you look at, the more references you check out, it's very likely you'll find a cartridge that's close to what you're trying to accomplish. And that'll save you time and money. It'll save you work in terms of making tooling, in terms of making reloading dies. It'll save you money in terms of ordering those things from someone. So when you go to design a cartridge, just remember, go back and look again and again and again to see what else is available, because there's almost always a cartridge that's very close to what you want that will require minimal changes. Keep in mind, you need to have a case that has dimensions that are appropriate to the project you're working on, and also that has the case capacity or the volume that's going to work with the project you have in mind. Those are two very important criteria. Now we're ready to move on with the next stage since we've finished our 358 Indy. But we have some opportunities here to talk about other types of wildcats you might be interested in working with, and this will give you some scenarios that are different from being limited to specific dimensions like we were with these state regulations. So we're going to look at a possibility here. On your left we have the 4570, and that's an original black powder type cartridge that has enjoyed popularity for a very, very long time. So let's say that you really like this cartridge, but what you're looking for is something with a little more punch, something maybe a little more modern. So you decide that you'd be willing to put it in any gun, and so that changes your parameters in terms of designing a cartridge. You're able then to go to any action and any pressure level really, and so it just frees you up. So we looked at the 458 Winchester as a possibility as a parent for this new Wildcat. Now the 458 Winchester is considerably longer, and the factory version runs higher pressures than we had in mind. You know, we're looking for something that's just a little better, has better loading flexibility than the 4570, and takes advantage of stronger brass. So by going to the 458 Winchester, we've opened up those possibilities so that we can try and achieve a little more loading flexibility and be able to get some higher pressures and higher velocities. So let's look at the next step. Here we have the 458 Winchester on the left, which is our parent cartridge, and then we have a proposed cartridge on the right, which is the 458 2-inch American. 2 inches is just a nice round number. We know it'll work in shorter magazines and will be a functional cartridge. This cartridge has slightly less case capacity than the 4570 we started with, but that's not going to be a problem because we've gained the ability to use different powders and load to higher pressures. So you'll get that gain in performance, that increase in velocity that you were looking for. It just so happens that this cartridge was already designed by a gentleman by the name of Frank Barnes. We just showed it to you for the very reason that we wanted you to understand that there are many reasons to design a Wildcat. This was just one. Now let's talk about another reason why you might build a Wildcat. Let's say that you have a favorite rifle that you've had for years, and for some reason the brass that you use for that cartridge has become hard to get. It's virtually unavailable. Now, you've looked around to see what other cartridges you could conceivably rechamber to, and it appears that there's nothing available on the commercial market, and so a Wildcat starts to become a good idea. You look around and there are no Wildcats in this particular area, so the first thing you do is start to look and see what cartridges are available that might allow you to go to a larger diameter and clean up your entire original chamber. So on our made-up example, your favorite gun was chambered in 358 Norma Magnum. In real life, that brass really is hard to come by. So we started looking for a piece of brass that would allow us to completely clean up the original chamber. The 300 Remington Ultramag will accomplish that. You can see here that it's considerably larger in all dimensions. The disadvantage is it's longer than our original cartridge, so we'll have to move the shoulder down and shorten the case to make it work in our shorter magazine. Now in reality, a client asked me to build this cartridge. This is the 300 Remington Ultramag cartridge, which we chose as a parent when we decided to replace our 358 Norma Magnum. So you can see by the replacement cartridge that we've reduced the length of the cartridge somewhat, and we've moved the shoulder back so that it'll function through our new chamber. Now the customer was happy with the results of this project, and he named the cartridge the 358 Yukon. It resolved the problems that he had and allowed him to continue using a favorite gun. Now for us, it's simply an example of one more reason why we might design a Wildcat. When it comes to doing drawings to represent your cartridge, there's a number of ways you can do it. You can start with something as simple as a pencil drawing.
and it'll totally suffice. All you're going to do is gather the pertinent data. You want your base dimension for the cartridge, you want the shoulder dimension for the cartridge, neck dimensions, length from the base to the shoulder, and the length from the base to the full length of the cartridge. So on this drawing we've represented those basic dimensions and very little else. You'll notice that the shoulder angle is delineated as well. So we're going to go on to another option. This is a computer drawn version, and it's the exact same cartridge. It's just we've used a piece of software to draw this cartridge out. Again, it's really pretty much the same dimensions. The advantage to this, of course, is it automatically adds in a couple of other extra things. A little easier to read. You know, it's going to give you your lengths for the neck and that sort of thing. So it has some advantages, but it's no better or worse necessarily than a hand-drawn drawing. Now, Climber Manufacturing in their product catalog includes something that's very useful. It's just a simple set of drawing templates, and they're available for all the different styles of cartridges, whether it be rimless, rimmed, or belted. You can either do a cartridge drawing, or as we're showing at the bottom here, you can do a reamer drawing. I usually recommend, especially when you're just getting started, that you do the cartridge drawing. It's the easiest one for you to do. You can measure directly off your brass and get real-world numbers so you know exactly what you're working with. So after using that, what you can do is you just photocopy those pages, and we took our same dimensions and just entered them in the appropriate boxes. And there is a little bit of room here for some extra information. It's not essential that you add this information, as the reamer maker knows how to do that. The drawback to this particular drawing is that it doesn't directly represent your cartridge. It's just a visual representation of a bottleneck case. So you're going to enter your dimensions, but it does not give you the direct visual representation of what you're designing. So just keep that in mind. Now we can go to the software and draw a cartridge, and what we have here is the 25 WSSM in the software, and we're able to modify the shape of this case on the fly. It's fairly simple. What we'll do is we'll go and select particular items. Like for right now we have the length dimension selected here. That's not going to do us much good at the moment, so we'll go over and select the neck diameter. We're going to resize the neck over here on the menu. So when we do that, it selects both the upper and lower measurement for the neck, so that we'll be changing those dimensions at the same time. We just simply go over to the up and down arrows. We're going to be increasing our diameter, and for a 358 we need to go to 386 is a normal outside neck dimension for loaded ammunition, and that's what we're representing here. So we'll just click the up arrow until we get to 380, and we move over 1 thousandths and we'll get to 6. Okay, now we've changed that, and what it does is it changes the shoulder angle at the same time, so we're going to have to make a correction for that. We've decided already that we're going to keep the same body of this case and simply rework the neck and shoulder area. So we'll now correct the shoulder length in order to get the shoulder angle back to 30 degrees where it started. So we just select that length. That's the junction of the neck and shoulder. Drop over to the down arrow and move that down, and you can watch the angle change as we bring that junction down. And we're going for 30. I went a little too far, so we just go up. 31, that's 29. So you just, by switching to the different arrows, you can modify how much you're changing it. We're down a little bit, so we need to go the other way. Okay, we're at 30 degrees. So this gives us a representation of the cartridge pretty much as we want it. The only thing that's wrong right now is the length. So we have a base diameter and a shoulder diameter that will function with us. We have a neck drawn for 358 caliber so that it'll accept the bullet. And then we're going to have to come back and shorten the neck in order to meet our dimensions. Let's take it down to 1.61, which will be just a little bit shorter than the maximum dimension, and that allows for some brass stretch, and will keep guys out of trouble in that respect. So we'll just again select the length, and shorten it up. And there we are at one. Oops, I'm in the wrong column. Move over one more. There we go. 1.61. So now we have a dimensionally correct drawing for our cartridge. And all we need to do is get the case capacity for this specific drawing so that we know how to compare it. So I'm going to move up here to the bullet seating depth, just like we did before. We select that, and then we have to run to the other side of the screen to change the seating depth. We just go up a 1,000th to get that, and back to the left again, and we're going to look at with bullet. We have 59.8 grains of case capacity. So we actually have more case capacity than we did with the 358 Winchester. Was 58.7 grains. So it's not a great deal of case capacity change. It's probably small enough that you wouldn't see any real difference ballistically, but it does meet our minimum requirement. So the drawing's complete, the dimensions are correct, and we're ready to print it out. However, there's nothing wrong with the plain old hand-drawn drawing. The reamer maker can work from this and give you a perfectly good representation of your reamer. Just make sure your dimensions are correct, because he'll build what you tell him to. Now, when you send that off to him, he's going to send you back a finished drawing. Pretty cool, huh? This is going to be something that represents everything he needs to build your reamer. Now that the drawing's out of the way, it's time to go to the next step. We're going to compare our cartridge to other existing cartridges and make sure we're not repeating history.
We're ready to start talking about steps 4 and 5. Step 4 is the process of comparing our cartridge to existing cartridges. Grab your research materials and go back and look. We need to find out if this cartridge is going to duplicate something that's already in the market, either commercially or as a Wildcat. Now, once we know this, we can make a decision whether or not we want to build it. And it's up to you to decide that. It doesn't matter if you've got a cartridge that's very similar to something else. If you decide that it's different enough and it's something you want to build, you're free to do that. After all, you're the king. Now, the idea here is we're trying to make you fully informed. We don't want you to show up at the range someday with your brand new Irgersplitten Loudenboomer and have some guy lean over your shoulder and say, wow, that looks just like a 308 Winchester. And you suddenly find yourself in an embarrassing situation. Instead, you'd be able to turn to him and say, well, yeah, this is very similar, but I'm doing it my way. You're probably asking, what is this unassuming little tool? Well, it's a single flute chamber reamer, and this is where we often call these a cannon reamer or a shell reamer. And you're probably looking at this. I know when I teach my classes and I pass these around, the guys always say, are you kidding me? We're actually going to try and cut a chamber with something like that? It doesn't look like it would do anything, but you'll be amazed just how fast this will peel up chips and cut. They work every bit as good as a multi-flute chamber reamer does. Now, the things you should know about these, they can be used for a lot of different things. You can use them as a chamber reamer. You can make them specifically to do neck work, throat work. You can make them for resize reamers. Just about anything that would use a form cutting tool, you can make a cannon reamer to do that particular job. Now, the tools you need to make these are pretty straightforward. Any shop that has a lathe and a mill, you'll be able to make one of these. You don't even really have to have a mill, because you can use a grinder to do the half profile. And you will be using a grinder to remove the excess material from the reamer later in the program. Let's talk about the pros and cons of a cannon reamer versus a multi-flute conventional reamer. The pros are that the cannon reamer itself is cheaper to make. It takes a very small amount of material. They're highly versatile. You can make them in any shape or length that you need. They're easy to produce. It doesn't take a huge amount of skill. If you can run a lathe, you can easily make one of these. The cons are that these reamers have a relatively short life. They're not good for production work. One possibility is you might warp it during heat treat, and of course that means you're going to have to make another one. I recommend that you just plan on having to do that, because I've made several duplicates myself over the years when I've made one of these and it warped during heat treat. Large diameter reamers can be a problem because they tend to grab in the workpiece. So when you make one of those, you'll probably want to make it in a 2-flute, and we'll show you later how to do that. Another negative of the Canon reamer is simply that they do take a fair amount of time to make. If you're in a shop where you have a lot of work booked up and you could be making good money each hour, then it's probably not cost effective for you to make these reamers, and you'd be better off to order one from a custom maker. Either way, we can show you here how to make them. It's a lot of fun, and it's a great way to build things at a low cost. It's time to talk about our resizing reamer and the dimensions we're going to use. The reason they're called a resize reamer is because it's used to make the resizing die. We will also use this reamer to make forming dies, and we'll talk more about that later. Now let's talk a little about the dies themselves. Resizing dies are somewhat undersized compared to our brass drawing. Now the reason for that is when you fire brass in the chamber, it's going to expand and be somewhat larger, and in order to make it functional again, we have to shrink it back down. Now factory dies that you normally buy are oftentimes sloppy, and the reason for this is it gives them complete reliability and they don't have to worry about whether the brass will feed properly or not. But you can get better accuracy by having closer dimensions. And you're God here, so why not close up those dimensions and get better accuracy? Now we'll go to the whiteboard and talk about the dimensions for our cartridge. Now what we're going to start with is the base dimension, which on your drawing is going to be essentially the base dimension of the cartridge. And when you make the taper of your reamer, and this is the representation here of a complete reamer, you want to go ahead and continue the taper beyond the base point of the cartridge itself. The reason being, this will allow you some flexibility. If you run into any problems, you could actually make some corrections without having to make a whole new reamer. But the main point here is the dimensions we're going to give you. At the base, you're going to want to be 1/1000th smaller than you are on your brass drawing. And the purpose of that is to bring the brass back down to the correct dimension so that when it springs back, it will end up being right on the dimension for your brass. Now at the shoulder, we're going to have essentially the same thing. We're going to have -1/1000th, and the advantage to that again is it'll bring it back down dimension, spring back a little bit, and it'll come right to the dimension of our brass. When we get to the pilot and neck, the reason it's labeled this way is because on this reamer we're making the pilot and neck dimension exactly the same diameter. It will be -0.004 from our brass drawing. The reason for this is to shrink the brass enough to get good neck tension and allow us to grip the bullet properly when we load the brass. The other thousandths that is in there is specifically for when we ream, the pilot has to have enough slip in the die itself, in the pilot hole, in order to function properly. So we're adding the 1/1000th there in order to be able to set the proper dimension inside the die when we ream that hole. Now let me show you a couple different ways that you can make your reamer. This is the same reamer I showed you earlier, so let's take a look at the profile and get an idea of what it's going to look like. Now I'm showing you the face that's been cut away, so this is a half profile. When you look, you can see that we continue our taper beyond the end of the chamber. The end of the chamber would actually be about here, but the reamer is longer than that. Now as you come up the profile, we have a nice sharp shoulder, and then we drop down to the neck area. And when you look at this neck, you can see we have a nice 45-degree shoulder at the end of it, which is how pretty much all reamers are done. And you can see there's no throat area cut, that it's just cylindrical in shape, runs right out into the pilot. Now there's more than one way to make these reamers. When I first started out, I made all my reamers this way with the neck inclusive. And there's nothing wrong with doing it that way. It's a very precise method, but it adds a lot of work to the process of manufacturing the reamer itself. I learned later that it was a lot simpler to make my pilot, and the reason we had on our previous drawing the pilot / neck is because you can make your pilot the same diameter as your neck. Now you're going to say to me, well then how am I going to cut my neck? Well, that's not a problem, because you're going to take a decimal reamer. First you'll drill the die blank out with a drill bit, and then take an appropriate decimal reamer for the diameter of your neck and ream that thing out, and that'll give you the actual neck diameter in your die, and then the reamer doesn't have to cut that. That saves you the trouble of actually having to make this entire area on the reamer. Now, not only are you going to save the effort that it takes to machine this in and get the correct dimensions, you're also going to save time when it comes time to doing the relief grinding. So, it's a huge savings in the setup time and calculating out all these numbers. Now, why don't we look at another reamer? This one, you can see here we have a nice long taper. You can see the beginning of the shoulder here, nice clean angle, and then we have no neck whatsoever on the pilot. Now, the reason for that, of course, as we discussed a moment ago, is that the die blank itself can take care of that. All we have to do is ream the die blank to the correct dimensions, and this pilot will just run in that hole and cut us a nice clean body. The neck is taken care of on its own. Think of how tedious it would be to have to turn a neck on a small diameter like this and then have to do the relief grinds. Take a great deal of time. It takes a lot of time on a larger reamer as well, so we're really talking about simplifying the process, allowing the die to take care of the neck. Now, I would recommend that when you go ahead and start this process, that you practice with one that actually has the neck built into it. And you should do it 2 or 3 times, because you're not going to get it right the first time. There's nothing wrong with making mistakes, and frankly, drill rod's pretty cheap. So making mistakes isn't a problem. You're going to learn more from that than you do from your successes. And I'd recommend that you go ahead and do some practice pieces in advance, because you don't want to be on the clock when you do your first reamer. Now, the reason we talked about doing the cutting edges on the neck and that's a good thing to practice is because someday you're probably going to want to make a chamber reamer this way. And I'll talk more later about the other features you need to include in that, but that'll be good practice and you'll be ready for that later. So let's go make a reamer. Now we're going to talk about the machining process of actually making your reamer. Now, this particular blank is already taper turned for a specific taper, and it already has on the back end your drive end, and the drive end is always the same size, and we can hit that number later. But basically what we're showing you here is that you turn the taper, always make it longer than the actual cartridge itself so that you have room to move the cartridge up and down the blank if you need to. If you make a mistake, it'll give you some room to save your own bacon. If you're not used to turning tapers, don't worry about it. It's not that difficult. After you've tried it a few times, you'll see that it's just about as easy as turning threads, if not easier. And it's actually kind of fun. Now, we're going to look at another example here. Okay, this is the profile of a finished turned reamer. We have a pilot dimension out here. We have our neck dimension here, shoulder, and the body taper. So this is a completely finished version of the reamer we were talking about. Once you've turned the taper, it's time to do the neck and pilot. Now on this particular reamer, because we have both a neck and a pilot, you'll turn the entire length of the pilot to the neck diameter, stopping at the point of your neck-shoulder junction. Once you've done that, you'll mark out the length of the neck, and then come back and turn your pilot to dimension so that everything is in line with the bore. Now, once you have your neck finished and your pilot finished, you can reset the compound on the lathe to the correct shoulder angle, and what you'll do is just by hand run that compound in and out to cut the shoulder angle. Now the precise point where this shoulder ends in terms of the dimension of the outside corner of this shoulder is not super critical. We set a dimension on our drawing and we want to be very, very close to it. But if you're off by a 1/2 thousandth, don't panic, because this is your baby and you can do it any way you want. You don't have to make a whole new reamer over a 1/2 thousandth or something. So it gives you some flexibility. Just remember you're king and you can do it the way you want. Then finally, we're going to set the angle of the end of the case mouth at 45 degrees because it makes it easier for this reamer to actually cut if we put a bevel at the end. Okay. Now let's go ahead and talk about the relief cuts that we make to the reamer so that we can actually make this reamer cut. What we have here is a representation of an end view of the reamer. So we have the outer diameter of the reamer, and then we have the neck diameter that you've turned on your reamer. And what we're going to do is give you a representation of what it looks like after it's been milled. If you're doing a single flute, you're simply going to draw a line halfway through the reamer, and it needs to be plus or minus 10 thousandths from the center line of the reamer. The reason being that at that center line is imperative so that your reamer will cut a clean edge. If it's too far one way, it'll cut undersize. If it's too far the other way, it'll cut oversize. So just remember that you need to be close to center line, but it doesn't have to be exactly perfect. And the simplest way to do that is when you make those cuts on the mill, you can just measure right across your biggest diameter and see if you're halfway. Okay? Now if you're doing a two flute, it's a little bit different. Make sure you keep in mind the rotation of the reamer. We know it's going to rotate in this direction, so our cutting edges are going to always be rotating in that same direction. This will be our first cutting edge, so it is going to be 90 degrees essentially from the circumference. So we head in towards center line and come up, and then this cutting edge also coming in towards center line. And it's essential that we be on center line for the same reason we were over here. If we get below center line on our cutting edge, we'll cut too large. If we go above center line, we'll cut too small or not at all. So keep those things in mind. Now once you've made these cuts, of course, the reamer is going to look a little different. It's going to be more like this. We'll cut this other part away. So you're going to end up with a profile that looks something like that when you're looking at it from the muzzle. And you note that the two don't cross in the middle, which would cause a weakness to the reamer. So when we start the relief grind process, we need to think about a couple things. First of all, behind the cutting edge, you want to make a relief grind that's just a little deeper than probably the rest of it. And what I usually do is I come in and I use the radius of the wheel to cut about a 20 thousandths deep groove below the cutting edge. And the purpose of this groove is to give a place for oil and chips to go to so they won't get caught behind the reamer and cause scratches or galling. I leave about a 1/16 of an inch is going to be the edge that we're going to sharpen later. I leave that right at the cutting edge. So once we do that, we'll come back and we'll also grind away behind this all the way along here. The only place the reamer is going to touch when it's finished is on the pilot and on the cutting edge. So we're going to shrink the profile of this reamer except for the diameter of the cutting edge. That's the only dimension that is going to end up remaining full profile. Now we'll do the same thing on this one. We're going to do another 20 thousandths relief grind down here, and we'll also do a relief grind behind the cutting edge all the way around, again reducing the profile but leaving about a 1/16 of an inch up here at the cutting edge. This area of relief behind our groove is probably only 10 or 15 thousandths. It's not as much as we cut here, but it has to be enough so that it clearly does not touch and chips can't get caught in between. So just figure 10 or 15 thousandths and that'll work. If perhaps you do have something touch, it'll show up right away. There'll be a shiny spot on the reamer and you'll feel it. The reamer won't want to cut clean. So you'll be able to go right back and grind that off. Now when we go to the other reamer, the single flute reamer, the same system applies. We're going to go behind the cutting edge and we're going to grind away our 20 thousandths deep area. Okay, so that you leave about a 1/16 of an inch at your cutting edge, and then we're going to relief grind the entire circumference behind the cutting edge all the way around, reducing the dimensions all the way around this reamer. And again, the only part of this reamer that's going to touch when it's actually cutting is the pilot and the cutting edge. Nothing else on the reamer touches. If it does, it'll cause galling and it'll cause problems in your chamber. It will not be accurate, it won't cut well. So just remember, only two things: pilot touches, cutting edge touches. Your cutting edge will be about a 1/16 of an inch wide at this point, and we'll go back and hand sharpen that in a little bit. We'll show you how to do that. Now that I've taken you through the entire process of turning, cutting your major relief, and relief grinding your reamer, let's look at a couple of specific details. This particular reamer is completely finished in terms of our machine work. It has been turned, it has its taper, has a neck, and the major relief grinds have been completed. Notice this is a two flute, so we have one here, and you roll it over and there's a second cut. What I didn't tell you before was that this is the stage where we'll stop and heat treat the reamer. The reason for that is it gives us a better finish once it's hardened, and it'll be easier for you to get a good consistent grind on the tool without cutting too far, and you'll get a nicer looking, better cutting reamer when you're all finished. Let's look at a couple of other samples. I wanted to show you this reamer because it's a different configuration than the other reamers that we've made, but the process is exactly the same. You'll note that you can see the effects of heat treat on it, but in terms of the technology we use, the shape of the reamer and the way it's been relief ground is exactly the same as what we've taught you on the other reamers. Now, here's the single flute reamer that we've looked at before. I want you to notice that there's a bit of a relief grind on this flat, and the purpose for that is to give us a better, cleaner cutting edge. It'll pull cleaner chips and produce a better finish in the die or in the chamber. Now, on the back side you can see some of the relief grind behind the cutting edge, and then you can see that it has been relieved all the way around so that nothing will touch. I almost always do this relief cut when I do a single flute cutter, but it's not absolutely necessary, and when you do a two flute cutter, you really can't reach in there and do this grinding, so don't worry about it. Now, if you don't understand anything we've covered on this section, it's a good time to rewind and look it over again, because it is a pretty complex group of operations. And this is the heart and core of the entire process, so you need to make sure you understand it so you'll get a good quality die or a good quality chamber from your finish reamer. Now let's talk about the heat treat process. We mentioned earlier that there's two types of materials you might use to make these reamers. Air hardening steel is very useful from the standpoint that it doesn't deform as much, it has less shrinkage, and it's very easy to use. The disadvantage is you really need a heat treat oven to make good use of it. Now, in most shops who are going to try this process, you probably don't have access to a heat treat oven, so we use oil hardening drill rod. The advantage to that is it's very low tech. All you're going to need is a can of oil. I usually use non-detergent 30 weight oil that I pick up at the local auto parts store. You're also going to need some kind of a torch. You can't get enough heat out of something like a MAP gas torch. You're going to need an acetylene torch. You want to use a fairly large tip so that you can spread the heat evenly and not have hot spots in your tool. If you end up with a hot spot, you're going to promote warping, and that's just going to discourage a good quality tool. Let's look at what it takes to wire one up and get it ready to heat treat. Now here's a blank that we've looked at a couple times already. It's already completely formed. We have our outside contour as well as our relief cuts. Then I just take a piece of simple baling wire. I've put a little hook in the end of the baling wire so I can put it in our center hole at the end of the reamer. And then you just simply wrap it around the tool and get it wired nice and tight. And you'll just have enough wire so that you can suspend this so that it'll remain straight up and down. This is important because if it's not straight up and down, you have potential for warpage when it goes into the oil. Anytime you enter the tool into the oil in the heat treat process, it cannot swing side to side, as this will likely cause warpage. Now, a two flute reamer is a little less prone to warpage, but the rules still stand. The other little trick that I use is I will put this piece of wire in my drill press, put the can on the table of the drill press, and when I'm ready to plunge the tool into the oil, all you have to do is rotate the arm of the drill press and run it right in. Once you've finished the heat treat process to this point, you're going to take the tool out as soon as it's cooled enough to handle, unwrap it, and check it for hardness. You can either use some of the files that are on the market that are designed for checking hardness, or you can take a simple bench file and just check the outside surface of the reamer. If the file slides across without actually cutting, you have a hard reamer. If it cuts into this tool at this point, it's not hard enough, and you're going to have to stop and run the process of heat treating over again. This concludes what I have to say about the heat treating. Just keep in mind you want to use even heat so that you don't promote warpage that way. When you go to the cooling oil, make sure you don't swing side to side or touch the bottom of the can, as both of these things can cause warpage. That's pretty much it, so let's go to the grinder and do some relief grinding. You can see we've set up to start our grinding process, and you'll probably notice that this is a very small bench grinder. That really doesn't matter because we don't need real fancy tools to do this process, and that's one of the points we want to make. Now, the first thing I did was I took our blank that we've already finished all the machining on, and I scribed a line along the cutting edge. Okay, so now when you look at this reamer, you'll see that I've scribed a line starting at the beginning of the neck, runs all the way back along the shoulder and along the length of the body. All I have to do is remember not to grind beyond that line because this will be the cutting edge up above here, above that line. You ready to go? Let's start. When I start grinding these, I try to keep the reamer parallel, the reamer's surface parallel to the front of the wheel. We're not trying to cut any grooves or anything that would be out of concentricity with the reamer itself. So keep it parallel to the face of the wheel, and I always start my first cut right at our line that we just drew at the cutting edge. So I'm going to start so that I can see from above that I still have that 16th gap. I'm going to start at the shoulder, work my way all the way back along the body, and when I get to the back of the body I'll just go ahead and reverse direction and run back up this way, and then I'll stop and check and see how much I've cut. And if it's not deep enough, I can go back and hit it again the exact same way, again remaining parallel to the face of the wheel. Just run from the shoulder all the way out to the back of the reamer and then reverse the process again. As soon as you feel you have enough relief here so that you won't have to worry about chips and oil and things collecting behind the cutting edge, then you're ready to move on to the rest of the relief grind. You'll repeat the same process on the shoulder and on the neck. When you do the shoulder, it's just a little bit different. You're going to tip the reamer so that you're facing the angle of the shoulder to the face of the wheel. It's okay if the wheel undercuts a little bit on the back side of your neck as long as you don't cut up into your cutting edge. So just line yourself up with the shoulder aligned to the face of the wheel, and you're going to relief grind up to your scribed line. Again, relieving material so that there won't be any danger of this back part of the reamer actually engaging with the chamber or the die. So after we've done that, we can turn and do the neck, and it's the same exact process. We remove a groove right behind the cutting edge and then do a relief grind back away from the cutting edge. Okay? The only other step that you have to be concerned with is at the end of the case mouth here, at the end of the neck, you're going to want to also do a relief grind, and you do the same thing you did with the shoulder. Just match up the angle with the face of the wheel and grind from your... In this case, you still need to leave the cutting edge because it's going to have to cut that inside the die or inside the chamber. So make sure you stay back of the line again. And again, we'll just do a relief grind away from that line. Alright, let's just go ahead and turn the wheel on and go to work. Okay, we've ground right up to the line. We've clearly removed enough material so that we wouldn't have to worry about chips being stuck there. So now we can go to relieving behind this cutting edge all the way around the back side. Alright, I'm going to take the relief cut and run it over the back side like we've talked about doing. You can see that I still have a good relief groove here, and I've left my 1/16 of an inch cutting edge. So what I'll do is I'll use the relief groove as a place to stop when I rotate the reamer. So just go ahead and watch here. We'll start on the back side and work our way in. And I'm just going to move over and continue to do that. And it'll take a couple of passes to remove enough material to give us plenty of clearance. And actually, as I'm doing this, I'm deepening that first cut that I made a little bit. But it helps give me a nice, clean, finished look. It gives me plenty of clearance so I don't have chips trapped on the back side of the reamer causing me problems. Now think about practice while you're doing this. If you're going to be doing very many of these, it's probably a good idea to really get a technique down and get comfortable with doing it. So you might build a couple of reamers just for the experience of going through this process and finding out how your machines work and you know, how you're going to have to do this to get the finish you want. It's just valuable to get that practice in and not find yourself lost in the process when it's important to get the right one done. You know, if you're working on a paying job for somebody and the clock's turning, it's going to change your whole attitude about how fast you can get this done and how well you can do it. Now let's take a look. We have a good cutting edge left over. Still have a good about a 1/16 of an inch. And we've completely removed everything behind that cutting edge all the way around the body. Now we'll move to the shoulder, and while we're doing the shoulder we have to set the reamer at a different angle so that we are only removing the material on the shoulder. You want to be careful not to undercut the neck too much, but it's okay if the wheel touches this junction between the neck and shoulder. And the reason for that is we need that relief grind, because if it actually, if anything behind the cutting edge is able to touch, it'll prevent you from pushing the reamer into the chamber. So I'll just align the shoulder angle with the face of the wheel like we talked about. Go ahead and cut a relief right behind the cutting edge like we did with the rest of it. Gives us a nice starting point. Come back and just do the radius. Notice I'm just letting the machine do the work. I'm not shoving into it real hard or trying to force it to grind. Now you can see I got a little bit of material out of the neck, but not too much. And the whole idea there is that we don't want to create a fracture point. Now we're going to run into the same thing when we get to the mouth of the case, but we're going to do the neck first. So I'm going to do the same thing on neck I did on the body. We're going to do a relief grind right behind the cutting edge. We want to be careful not to bump into the shoulder too much, because if we ground too far back we could actually get into our cutting edge where that angle comes up. So just watch that, be careful about it. Make sure you get your relief grind deep enough so that it'll give you a place for chips to go. Just check it. Now I've got enough, so I'll go to the other side. And again, I don't want to cut too deep into the shoulder, but it's okay if I touch it. And we'll use that relief grind that we did first as a stopping point below the cutting edge. Okay. Getting a nice looking finished product here. Plenty of relief so we don't have to worry about chips. Okay. When the reamer gets a little hot, you'll know. You only have to burn your fingers once or twice before you decide it's time to cool that thing off. Now the last thing we have to do, we got plenty of relief here. I want you to see that we left our cutting edge. Have a nice deep relief grind right behind the cutting edge. You can see that hollow grind. And then we removed all the material behind it, so we don't have to worry about that. There's just two little things left to do on this particular grind. I'm going to come back up here on the shoulder and relieve this sharp angle a little bit, just to make sure there's a little more room for chips to escape. So all I'm going to do there is just radius that off. It does not need to be the shape of the cartridge anymore. That was just for us to create our cutting edge. Okay, so that's all gone. Just radius down real nice. The last thing we have to do is come up here and grind this junction with the neck and the pilot. And we have to have relief here because this is going to be cutting the mouth. This is where your mouth of your case would be, and it's actually going to have to cut in the die if we use this particular reamer. So we're going to just go in at an angle like we did with the shoulder. And you just watch when you get up to where your relief grind is, you stop. Try not to undercut the pilot very much because you're creating a fracture point. When you harden this reamer and you grind like this, you're creating a place like when you cut a piece of glass. If you cut a deep groove, it's an easy place to snap that pilot off. So just make sure you have a good relief. Try not to undercut it too much. Okay. Now we've completely done our relief grind here. There's probably one thing you notice about this reamer blank that you're concerned about. There's no discoloration from heat treat. The reason for that is pretty simple. We chose not to heat treat this reamer because we wanted to be able to grind it a little faster for you on camera. You probably don't want to stand and watch me grind for a long time, and there's no necessity to that. The process is identical, the techniques are identical, and you'll just get a little better finish actually is the main difference. If you were to do these relief grinds before you heat treated, it would be okay as long as you leave your cutting edge. But then if you choose to do that and it warps, you're going to be angry with yourself for wasting that time. So that's why we always heat treat before we do relief grinds, just to save ourselves that headache if we do warp the reamer. I'm very happy with the way this is turning out, and I think it would cut just fine as soon as we get it sharpened up. Now I'll show you how to do that in a couple minutes, but for the moment I'm going to set this aside and show you how to do a resharpening on an existing one flute reamer. This is one we've seen earlier. You can see that it has a little bit of a hollow grind, and it's been used some. You can kind of see those dark spots are places where it's built up some use and a little bit of wear. And so we're going to do a relief grind on this flat. The purpose of this is so that we'll get a good clean finish when we cut our die or cut our chamber. So let's go ahead and start the grinder up again and see how that's done. The way we do this is we put our face perpendicular to the grinding wheel. When you're looking down on it from above, it's very easy to see. And what you're going to do is you're going to start with it tipped back slightly from the wheel, and as you get a good grind on it, you'll start to lean it in a little more until the sparks start bouncing off the top edge of this cutting edge. We don't want to go terribly deep because that would change our dimensions. So please keep in mind that this is just a cleanup, and this is very similar to how you're going to grind a single flute to do this hollow grind yourself. So it's really the same process. We're just showing you that you can either resharpen or it's the process you use when you're making the reamer to begin with. I'm going to work it back and forth just like I did with the other grinds, and the purpose of that is to try and give me one nice even grind. And I can feel that I'm starting to get a groove that I'm working in, so I'll start tipping towards the cutting edge a little bit to expand that groove. And as I do that, you maybe can see that the sparks are starting to bounce off the top of the reamer rather than just slide underneath it. And as they start to bounce off the top, I know that I've brought that grind right up to that top edge. As soon as I feel like it's fairly uniform, I'll just stop and take a quick look at it. Well, we're pretty darn good. The only thing that we didn't grind is a little hand grind deal that I had done on this reamer originally, so that I could get the chips to cut away in a certain fashion. You could do these hand grinds, you don't have to. This hollow grind like we did here is perfect, and it'll remove the chips nice and clean and give us a nice smooth cut. You know, what I can't emphasize enough is that practice. I mean, this is a fun process. If you're interested enough in this idea of building Wildcats to buy yourself this video, then you're going to enjoy the process of trying to do this and improving your skills and getting better at it. You don't want to be under pressure the first time you do it for maybe a paying customer or maybe some friends watching you. So build those skills, get good at it, and you're going to enjoy it, because anything technical like this that's part of your hobby that you enjoy, building those skills is always a fun thing to do. Now let me change my setup and we can just go to the sharpening process. Okay, we're ready with our setup. We have a Versa vise here, and you're going to need some kind of a small bench vise to hang on to the reamer while you're doing this work, simply because it's really hard to do it in your hand. You need to be able to retain some angles and not roll over the edge, so a vise is pretty essential. Now, you're going to have to forgive me for a small mistake. When we finished milling this, I didn't get it completely deburred, so normally we would do this prior to the heat treat. So just forgive me for my humanity and we'll move on with this. So I'm just going to quickly deburr this edge, and it doesn't take much. We're just using a fine file. We're just going to take off those little burrs that were still there. All the big burrs are gone. We just had a couple little tiny guys standing up from when the mill was there. Okay. Nothing major, just if we have those standing up when we sharpen it, it'll just eat up our stone a little quicker, and that's not necessary. So now all we're going to use to do the sharpening is a small stone. This is just a square, standard, like an Arkansas type stone. You can use a diamond lap. They make them in several different grits, so you can start with a coarse one and move to a finer one. They work pretty fast, and they're very efficient. They'll give you a pretty broad cutting edge, so you'll get a nice finish. Now, when you approach the cutting edge, you want to make sure you don't ever roll on the flat side of the edge, on the cutting face. So in order for me to do this, I'm going to turn the reamer around so that I can get a better grip on it and work on it the way that it fits my hands. So you should still be able to see it pretty well what we're doing. Okay. That'll work for me if it'll work for you. So we're going to approach the cutting edge from the backside on our relief grind, and I always try to keep track of where that cutting edge, because like I said, you do not want to roll past, and because that will change the dimension and ruin the reamer. What it'll do if you do it in just one spot, you'll create what's called crown, which is a problem with the backside of the cutting edge actually dragging on the chamber, and that'll usually cause galling and pull material out. Sometimes it'll just leave a really ugly, rough chamber. So, but the basic method is start from the back side, and you can just see it change color as you're running the stone along here, and you are relieving some of this backside of this 1/16 inch that we left. And the reason we're doing that is you can't have that much material actually touching the inside of the chamber, but you do have to have enough material to get a full dimension. If we ground up too close to it, we'd have too many chances to grind into that and mess it up. So we leave that 1/16 because it just doesn't take that much hand stoning to fix it. So I am doing a little bit of a relief on the back side here, and I won't go right up to the cutting edge until I'm pretty comfortable that I've removed what I want from the back side of this little cutting edge we left. So our 1/16 is going to shrink a little at a time, and like I said, you can just watch the color change. It's real easy to see. At this point, we don't need to remove a ton of material for that relief, because all we're doing is getting it to where it's not dragging. We've got our chip relief behind that edge. Okay, let me take a little look at it here. We're approaching the edge pretty nicely. I'm going to roll it a little so I can see some more. We're going to cut a little bit more. And this is just a patience process. You know, you just have to watch what you're doing. Don't be afraid to cut too much, but at the same time, make sure you don't just roll right on over, because that's the last thing you want to do. You know, a little bit of patience goes a long ways. And if you do screw this up, you just get the honor of doing another reamer right away. So it's pretty critical to pay attention, and you know, if it takes 2 minutes longer, who cares, because I'd rather do that than spend another hour on the lathe. You know, I was thinking about this while I was sharpening this. It was several years ago, many years ago now, that I got into wildcatting, and I've been gunsmithing for quite a while by then. And I remember when I was in school, you know, we did some talking about the various types of cartridges a guy could design, and we looked at some of those designs, and of course some people built guns in those calibers, and that was all fine and dandy. But it was years later that I actually got interested, and I think it's a natural progression. I think when a gunsmith or a hobbyist starts shooting, they start out with standard calibers like 30-06 and you know, 45-70 or whatever it might be, and over time you develop an interest in various calibers, and you start thinking about what might shoot better or different. And what actually happened to me was I had a customer come into the store, and he had an idea for a Wildcat that he wanted to build desperately. And I was not too interested in building it, to be quite honest with you, until a few days later I got a sales flyer from one of the reamer makers that had a similar reamer on sale for the same family of Wildcats that he was interested in. So I called the guy and asked him if he wanted to do one of those, because I could get the reamer at a reasonable price and we could do the project for a little less money. And he said, sure, that'd be a lot of fun. So we went ahead and bought the tool, and it was a 375 Hawk, which is, it actually turned out to be the core of my line of Wildcats. So that first cartridge I didn't design, but what happened was he had become friends with the gentleman who had originally designed it, and he eventually introduced us, and I got permission to take over the 375 Hawk and turn it into a whole line of cartridges. And what happened initially, though, was we built the first gun for this gentleman named Graydon Snap. He's a good friend of mine. We hunted together for years after that. And the first gun was a 375 Hawk, and we got it all finished up, and you know, it's my job as the gunsmith to make sure everything functions properly. So I took that out to the range, and I took a chronograph with me, and I figured for sure there was no way that this particular cartridge was going to produce the results that were in the articles I'd read. And you know, I'm sure most people kind of get jaded and get the feeling that, you know, gun writers tend to inflate things, and no way could that possibly happen, or the gunsmith inflates it, and you know, and you, maybe we're a little too jaded, because some people are honest. Anyway, I took this 375 out, a couple test loads that I took out of the article, so I knew that they were supposed to be starting loads, but I had velocity ranges for them with the same barrel length and everything. Fired those first couple shots, and I looked at the chronograph, and lo and behold, I actually got more velocity than they reported in the article. And I was very impressed. It was a pretty exciting thing to have happen. And for those of you who have done that, it's just a feeling that you can't really maybe get across to somebody else until you try it. But it was exciting to have built the gun and got better results than what somebody else had with a similar thing. So immediately I returned to the shop and called the guy so he could come pick up his gun, and we got to talking, and he still wanted to build his version of it, which was a 35 caliber. So the 358 Hawk was born from that very meeting, the same day that we shot his gun for the first test fire. So while I was ordering the reamers, I just went ahead and ordered a 338 as well. So we did a 338 and a 358 immediately off of that first test. And that was kind of the very beginning of my interest in Wildcats. And that was probably 11 or 12 years ago. So I mean, it took me a while to grow into it, just like it does everyone else. I became very interested in other types of Wildcats. I got interested in the design process and what it takes to accomplish that. I started looking for resource material and studying. As a result of that, I've gotten very interested in the works of P.O. Ackley, and have done a lot of research into his past works. And you know, there's just a wealth of information about wildcatting that has kind of been forgotten. The old American Rifleman magazines are just chock full of information about wildcatting that took place from pre-war up until probably about the early 60s. And about that time, the magazine kind of changed, and it doesn't do as much reporting about things like that. But it's, you know, you can go back to those old magazines and read about things that some of these famous guys did, and it's so interesting to read it in a contemporary setting. You're reading about these guys as they did it and talking about the results they received. And then you can go and look at later writings and see how the stories have changed, and how other writers have maybe forgotten a detail or added a detail that wasn't there before. And that becomes very interesting. So I would just encourage you, you know, we talked about early in the program about research. That's some of the most fun for me in wildcatting, is to read about other people's work, to find out what it took for them to accomplish what they did. A good example of that is Harvey Donaldson. Harvey designed the 219 Donaldson Wasp and several other cartridges actually. But if you want to read about his exploits, so to speak, in one of the books that we mentioned earlier, it's called 22 Caliber Rifles by Charles S. Landis. There's a story in there that talks about the 10 years that it took Harvey Donaldson to develop the 219 Donaldson Wasp. And it's not that it took him 10 years to design one little cartridge. It's that he was willing to, he had an idea in mind. He wanted a cartridge that had a very minimal amount of powder capacity, so it had low recoil. He wanted a reasonable amount of velocity, and he wanted extreme accuracy. He was interested in bench rest shooting. So, and at that time, 22 caliber was really kind of the name of the game. So he tried multiple variations on the theme. He used different cases and different lengths. He tried different neck lengths, different bullets, and ultimately it took him a full 10 years to design what we now call the 219 Donaldson Wasp. And you know, I think I mentioned earlier when I talked about the 19 Hawk that I designed and that I was duplicating his work. I figured if he spent 10 years making all the mistakes, it was really foolish for me to spend any time making those mistakes. And that's why I tried to duplicate percentage-wise or volume-wise the case capacity versus the bore diameter that he used in his cartridge. And of course they're similar size cartridges, so it made sense to try that. Now I've just about got this finished. When I get down to the very tail end, all I can see is just the leftover lines from the lathe. I don't know if you can see that on camera. Let's try and... Okay, you can see I've got not much of an edge left as far as sharpening goes. And you can kind of see the lines from the lathe where it actually left little grooves. It's a little hard to see, but let me loosen this up. Just that kind of foggy look. What I'm seeing is actually little grooves. What you're seeing is kind of a foggy look there. And so what I'm going to do is at that point I'm going to very gently and slowly work that line. I'm going to keep it at this angle we have it at so that I can see it better. And this is where you could roll off that edge, so you want to take your time. And what I'm going to do is just slowly work a section until I see those lines mostly disappear. They don't have to be 100% gone because they're so shallow to begin with. There's really not much dimension to them. So just slowly work those. Clean your stone once in a while. And as the lines kind of disappear, then I know I've got a good sharp reamer going. And there's a simple way to test it. I'll show you here in just a second. We're almost there. Now this is the exact same technique we use on the single flute as we're using here on this two flute. There's no difference in how you prepare this cutting edge. There are one or two little things you can do to a two flute to help make it sharper, and I'll show you those as well. Because you can't do a relief grind on a two flute very well, the simplest thing to get a little extra sharpness out of it is you can take your stone and run it on this flat and just stone back and forth. And if you do it enough, you'll see a shine develop on here where you're removing the bumps left over from the machining process. And that will help give you a little sharper edge. It's not absolutely essential, but if you find that it's not cutting real clean, that's a way to improve it a little bit. You can just go in here and stone that flat until you get a nice uniform edge at your cutting edge. That won't be enough to change your dimensions, but it's enough to improve the cutting process. Now the simple test for whether we've got it sharp or not is just take your thumbnail and scrape it. And if it scrapes off some thumbnail, you can see that keratin there. That's plenty sharp enough to cut metal. And that's all it takes to make a good sharp cutting edge on one of these reamers. Now that you've made a resized reamer and you've made a beautiful reloading die, we need to talk a little bit more about using not only the dies but how you're going to use that resized reamer that you made to make some forming dies. Now you're going to start with something like this. You're going to have a long oversized cartridge and you're going to need to move the shoulder back. And of course there's different shapes and sizes, but this is the example we're going to use. So you want to reduce the shoulder length on your new case. So let's discuss how we're going to get there. We're going to go to this drawing. This represents, let's say, a die, and the inside blue color is where we're headed. The outside red is our parent cartridge. Now, we do this in steps. You're going to ream your first resizing die, the standard resizing die you're used to thinking of, and there'll be no other changes to it. So just set it aside, it's done. Now you're going to do multiple forming dies in order to move that shoulder back. We're going to choose a number. In this case, we're going to say that this shoulder has to be reduced 100 thousandths in total. So we just take 100, and I think I told you earlier in the process that the most you can move brass on its diameter in is about 40 thousandths in a pass when you're resizing. If you go more than that, you're going to start to see problems. So I'll show you a few of those problems here in a minute. But if you've got 100 thousandths you've got to work with and you can only go 40 at a pass, you're going to divide that up. I almost always make the first step 40 thousandths. And the reason I do that is because at that point it's when the brass is at its strongest and it's going to be able to take that deformation without any real problems. Now, we know that we've got 100 to work with, so we'll do 2 of them at 40 and 1 pass at 20. Now, because this final pass is at 20, you might be able to get away with using your resized die as the final die, and you'll have to experiment to find that out. So, let's just go ahead and look at what will happen. Our first die, the first 40 thousandths, we're going to come over here, and I'm going to leave this side alone so that you can remember what we started with. This side we'll make the changes on. So you're going to come in and you're going to take your resize die that you've cut, and it's cut to this dimension, the blue dimension, because you used your resize reamer we made to make that die. Now you need to do this in steps. So if you were trying to cram this piece of red, parent brass into this new shape, there's no way it would go. There's just too much brass here to move in one pass. So what we do is we take a drill bit and a chucking reamer or a decimal reamer. You can buy chucking reamers in individual decimal increments, and that's why they're called decimal reamers. So you can pick the exact reamers you need, or you can buy ones that are close. You might have a set that gets you close. As long as you're pretty close to this 40 thousandths, it'll work just fine. So you drill this hole out, and I always do the largest one, like I said, 40 thousandths. So I'm just going to basically do this. So now we have the body dimension we took off of our resize reamer, and we're boring out the neck dimension all the way through the die so that we have a clean pass for the brass to pass through. And what we're going to be doing is moving this shoulder right here, the red. Let me move that out of your way. We're going to remove this and resize it down to that blue shape. So we have just simply made this die bigger in the neck, but allowed us to shrink that shoulder and get this shoulder angle. Now, then we're going to do another 40 thousandths. So you just simply repeat the process. You're going to go to a smaller drill bit and a smaller decimal reamer to get this next 40 thousandths. So we're going to come in and we're going to be pretty close to our final dimension. Okay, and then that's going to remove this part of the shoulder. So now we have reduced the entire, I'll just go ahead and make that line solid so it'll make more sense. When you do that, you have moved your shoulder up, you've now created this angle, you're getting pretty close to your final dimension. Okay. Now our brass was smaller in the neck, so we're going to have to deal with that in a minute. But we've got this final 20 thousandths to do. Now you can, at this point, what I would do is I would take my resize die that I made and I would test to see whether or not it can do this final thing. And actually at each stage of this, I stop after I make each die and I do a test run with 5 or 6 pieces of brass. If they seem to be forming okay and everything's working well, then I just continue with the process. So you do that after each one, and you can take those, when you do the first half dozen pieces of brass, you can use those for the next step, and then of course the final step. And the reason I do a half a dozen or so is because inevitably a few of them get damaged in the process, and you want to have enough to be able to test without having to start from scratch and reset your, you're going to have to put those dies in the loading press to test them. So you get to this final step, put in the final normal resizing die, run a test piece. If it forms properly and everything's okay, you're done. If you see that you're getting unusual deformation, that the necks are collapsing, if the shoulder's trying to buckle out, and you're not comfortable with the way it looks, then all you have to do is make this final 20 thousandths die. And when you do this, I would make sure that you leave yourself just a little bit of dimension compared to your final resize. So you're going to want to make sure that the hole is slightly bigger than your neck diameter in your final resize. So 1 or 2 thousandths is enough. I mean, you just need enough so that your resized die can do the finishing job. And then you'll just make this last 20 thousandths, you're going to come in, you're going to make this into a solid line all the way up. And now it'll remove, when you resize, it'll remove that last piece of shoulder, and ultimately you're going to end up with this shape. Now remember, it's going to be the same on both sides. We did this so you could see, here's where we started, here's where we ended up. Okay? Now I have a couple of sample pieces of brass that I want to show you that show various forms of deformation. This first one was made by a student in one of my classes, and you can see, when we look at the shoulder area right here, that it's clearly buckling a little bit, and he's actually got a little bit of deformation on the outside of the shoulder. So you can tell that we're moving a little too much brass a little too fast. Now he understood this and knew that this would fire form out, and he wasn't concerned about it. He also knew that when he made his final set of dies, he could correct this problem. Let's look at a couple of others. I have, this is the 17 circus midget that we talked about earlier, and remember this was an exercise in seeing how far you can move the brass, so it kind of gives us a good example of the failures you can have. you can kind of see that this outside corner is buckling out. It's been pushed way too hard. You can also see, as you move up the shoulder here, we have actually a secondary shoulder, and that's because it was so hard to push this into the die that we actually stopped here and didn't get a full size down to the shoulder. Now, when you look up here at the top, you can see the mouth of the case has flared out somewhat. That's a result of the corner in the die was a little sharp where the neck and the shoulder meet, and that causes this brass to peel around the corner the same way that brass will peel, or I'm sorry, the same way that if you were to make a Christmas ribbon and you zip it with the scissors and it causes it to curl up, it's the same effect. The brass is going to do the same thing when you drag it along that sharp corner. The solution to that is pretty simple. You can do a little bit of final sanding afterwards with some 400 grit paper to clean up that corner. Just run a mandrel in there and clean up that corner a little bit so it's not so sharp, and that'll resolve that issue. But this gives us a pretty good example of several forms of stress that are created. It's a good example of how brass thickens as we come down in size. This was the normal neck diameter or neck thickness on this type of brass would probably be about 12 or 12.5 thousandths, and here it's considerably thicker. This is probably on the order of 25 thousandths. So you can see that when you reduce brass, you are running an opportunity to build up quite a bit of thickness. So keep that in mind. Go on to another example. This is a caliber 10-222, so it's a 222 case neck down to 10. There's a few things you can see on this piece of brass that are kind of interesting. We can see that the case mouth, you can probably tell here that it's not completely parallel. It has a little bit of an angle to it. That's as we're going down in size, the brass is being pulled down too, and the weakest side of the case is going to pull down with it. So this case hasn't been trimmed to have a square mouth yet, it's just been sized. The other interesting thing to me is you can see the steps we went through to create this shoulder. Each of these little lines, or little bumps you can kind of see reflected in the light here, is one step that we took to move up in the process. So that's a good, this one turned out nice. There's no stress, there's no bulging, but you can see clearly that we went through several steps to form that shoulder. Okay? Now, this is a large case, and the attempt here is very similar to our 358 Yukon we've been looking at. The idea behind it is to move the shoulder down, shorten the neck, and get a shorter case when we're finished. Now you can see here that we were getting enough stress on this case that we actually caused a buckle in the shoulder. And that's a sign, again, that we're pushing too hard. This can also be caused by a little too much lube. So if you start to see this sort of thing, check and make sure you didn't overlube the case during the sizing process, but most likely this is going to be stress from moving too far too fast. Okay? And the solution again is just make another step die to reduce the amount of stress you're putting on that shoulder. And I've got one more. This one is actually the same cartridge as the last one you saw. This is finish formed and of course with a bullet seated. You can see a line here where there was a buckle where the shoulder had been pushed out a little bit in the forming process, and when this was fire formed, it was removed in the fire forming process, but the line's still visible. You can also see a little bit of stress along the shoulder. These lines that run along the length of the shoulder are stress from the reloading process. They really don't hurt anything. They're kind of ugly, and if you can avoid this, you make a better looking cartridge and you look more professional. So when you see these things, keep in mind that you're pushing the brass a little too hard. Okay? We do need to talk about another factor on our drawing here. We ended up with a neck that is, on our parent case, is a little smaller than our finished blue Wildcat case. The solution to that is the expander ball on your resize die is going to take care of expanding that neck. Now in an extreme case, I have some examples of how we can Wildcat a case by expanding the neck up and retaining the same shoulder angle. So it's sort of the reverse of what we did here. Here we reduced our shoulder, moved our shoulder back one step at a time until we got to the desired shape. The other way that we're going to look at right now is to increase the neck diameter retaining the same shoulder angle. So we're actually just pushing this neck diameter out this way and keeping the shoulder angle. So let's take a look at a couple of those.
This is the cartridge we started with at the beginning of the course was the 25 WSSM, and we're going to turn it into the 358 Indy. So this is the very first step. This is the factory piece of brass. It's a 25 WSSM. The next one in line is where we have expanded it, and I tried to go up as far as I could in each step. This is about an 8mm neck, so you should be able to see an 8mm bullet in that case. And I found that I could do that without collapsing the shoulder or without tearing the brass. And those are the two things that are likely to happen when, the two things that are likely to happen when you're expanding the neck. A tapered expander ball is required for this process. If you've never seen one, the manufacturers make various styles of them, or you can make your own, and it's simply a very shallow angle on the front of an expander ball. About 10 to 15 degrees is perfect for expanding brass. Of course, you'll have to lube the inside of the necks to make it work. Now, the next step for this cartridge was to go to 375. And at 375, the reason we did that is because this brass has the problem we've talked about before about getting thick in the body area. And it's even thick up on the shoulder. So the idea that I had was I'll go ahead and expand it up to 375, and then when I turn what I chose to do was turn the outside of the brass in order to remove that thickness. The advantage to doing it when it's 375 is when I go back and resize this brass, I actually, this is after I've turned it, and you can see the turning actually runs down into the shoulder just a little bit, and that gives it the proper thickness all the way down, and it also thins it in the area where it's going to be the junction of the neck and shoulder. So on the first few firings, I don't have to worry about that thick brass rolling around the corner and pinching my bullet in the neck, changing neck tension. So that is that step. The next thing we do then is take that piece of brass and size it back down to 358 caliber. Now on this one you can see that it's been in a die. It's a little bit scratched because we're using an unheat treated die, and you can see where we turned. There's just this little bump on the shoulder, but you can see it's below the junction just a little bit. And again, that gives us the advantage of having thin brass a little further down so we don't run into a problem. And of course the final is we take that sized piece of brass and seat a bullet in it to see what it's going to look like. And it's really a very simple process to make a batch of brass like we have here. Just takes a little bit of time. However long it takes you to change dies, change expander balls, is how long that's going to take. The turning process can be done on a regular lathe, which is very time consuming. You can do it between centers. The best way to do it is to get some kind of a brass turning tool that uses a mandrel and just turn your necks. And it's just that simple. So now that we've talked about forming, it's probably a good idea for you to just think back on the few things we talked about, which was watching for deformation of brass that's not normal. When you see those things, it's pretty simple. You just have to slow down, figure out what the problem is. Sometimes it could be the brass. Sometimes it'll be that you didn't make enough step dies to do your sizing process. And every type of brass is different. It's either going to be heat treated differently, or it's going to be thicker or thinner. So that's the thing about wildcatting, is you have to kind of fly with it. You have to find out what works with the particular design you're working with. I'm sorry I can't hold your hand through the whole process. I'd like to, but I think you'll have a lot of fun learning. I know I had a lot of fun. Each step of the way I learned something, and like most people, I feel like if I learn something every day, I'm still alive. Now that we've pretty well covered forming brass, I thought I'd just go back and touch on a few things. It's really important that you pay attention to the deformation problems we've talked about. If you see brass that's overly stressed, then you know that you are pushing it too hard. A simple fix for this is if, let's say you started with that first die at 40 thousandths reduction, and you see that you're pushing the brass too hard and it just doesn't look right. It's pretty simple. You just go back to your lathe and you're going to ream out that hole maybe another 10 thousandths, and go back and try it again try and resize that piece of brass again, or new piece of brass, to get that form. If you don't see the stress problems anymore, you've solved the problem and you can move on. You also, in the process, are saving that one die and using it so that you don't have loss. You can do this
in various steps. If 10 thousandths is not enough, do another 5 or another 10. Whatever you feel from what you're seeing on the brass is appropriate. Once you've got to that point, then you can use that number for the next die. So when you make the second reduction die, if you found out that 30 thousandths works, then you'll do 30 thousandths on the next step, and so on and so forth. Now, just because that worked on that particular cartridge doesn't mean that that strategy is going to work when you get to the next one. So be prepared to try it each time. The different brass you use, the different designs are going to cause changes in how the brass forms. Just be ready for that. It's part of the charm of the process. It's why you get into it. It's so you can learn to solve that challenge. Now, we talked to you earlier about making a chamber reamer versus making a resize reamer. The process is exactly the same. You're going to make the same reamer the same way. The only difference is dimensions. So here we're going to just show you those differences. Now, this is the same basic dimension or drawing we used before. Your base dimension of your cartridge used from your drawing that you did originally on the chamber is going to be +2 at the base. On the shoulder it's going to be +2 thousandths, and on your neck this entire area will be +4 thousandths, and that's to allow expansion for the bullet to escape. When you come to the throat area, you need to keep in mind you have a couple of choices. You can either put the throat on this reamer yourself, and the simplest way to get those dimensions would be to find a drawing from one of the reamer makers for the same cartridge or for the same bore diameter, and that'll give you the SAMI specifications for diameter, length, and lead. When it comes to the pilot of the reamer, remember it has to be able to sit on the lands of the barrel. So you can take some pin gauges or some other form of measure and check the bore diameter so you know what dimension to make this pilot. Generally, there are some standard dimensions you can pull from your research that will give you this information. If you don't want to put a throat on your reamer, then just go ahead and use a throating reamer. They're readily available from the manufacturers, or you can rent them from one of the rental houses. Okay, we've moved to the lathe and we're going to do some cutting on a die so that you can see that our reamers actually do remove metal and make chips. We have a 2-flute reamer here to the same design that we talked about before. Let's take a look. So here's the drive shank. You're going to need that on all reamers in order to be able to use them. You've got our continuous taper for the body, shoulder angle. This one has a neck on it, and it has a relief cut because it's a 2-flute that only goes part way through the reamer, and a nice long pilot. It's important to use a floating reamer holder because it keeps your reamer in alignment with the die body. Now if you didn't use one of these and your tailstock happened to be out of alignment, it would cause you to cut an oversized bore in your die or your chamber, and this would be, of course, a problem. So let's go ahead and install the reamer in the tailstock, and it's a pretty simple matter of using a set screw. Okay, we're all solid. Now you can see that the floating reamer holder is able to move in all directions. Okay, now that we've got everything set and ready to go, we'll put a little cutting oil on our cutter. Be liberal with it because that's what's protecting it. And we'll run it up into position here, get us close. We're ready to go. Lock down the tailstock, and let's turn this thing on and get it going. Okay, so we're just going to align the pilot so that it goes into the bore. We'll run that right up in there. And we're going to start to cut. Here we go. See little chips already starting to come out. I usually go about 50 thousandths on that first little cut and stop, back it out, take a look at what we're getting. You can see that we're getting a nice clean hole, and the chips are starting to form nicely. So we clear things off, put some fresh oil on, and then of course we'll run our tailstock back in there so we can cut some more. Okay, so we align our pilot with the hole, get it up close, lock the tailstock, and start cutting. And it cuts very smoothly. You could feel very little resistance. Usually at this point I still only go about 50 thousandths and stop and clear again. Okay, we're going to pull it away, clear it off. Some more cutting fluid.
We're ready to go. Okay, we're going to go ahead and make another cut. I'm just going to start getting into the shoulder very quickly here. And once it does that, we can usually just go ahead and go right up the shoulder and watch those chips form. Okay, there they come. Looks very nice. Okay, let's stop right there. So we'll clear this out, clean it off once again. Fresh cutting oil. And we'll go back at it. All right. So we're going to go back in. You can see we're pushing out some nice chips now. Amazing how much a homemade reamer can do. Every guy I've ever taught this method to has been absolutely amazed that you could peel off this much metal with something he made with his own hands. Okay, let's pull it out and take a look at our die. Okay, you can see that we've got a nice clean shoulder started. You can see that we have a nice neck down inside there. The reamer's cutting a very nice finish, and you couldn't ask for much more from any tool, let alone one that you made yourself. Okay, the reason we stopped here was because at this point you could see the finish we're cutting, and there would be no point in finishing anymore. Another thing that always comes up at this point in the process, people ask what the headspace is going to be on the reloading die. It's very simple. It's always 130 thousandths. And the reason for that is your shell holder is 125 thousandths high. The extra 5 thousandths is to allow you to set headspace to match your gun. And almost all manufacturers of reloading dies do that. So just add the 5 thousandths, call it a total of 130. You'll be able to move your shoulder up and down a little bit if you need to in order to match the gun. And that's all there is to it. Now that we've finished the entire course, I thought we'd take a couple minutes to talk about some of the important points that we've covered. The first thing you want to think about is the design process. When you start out, you're going to have an idea or a concept. Now the whole world is open to you. You're really the king here. You can pick any idea for any reason. If you want to put a specific cartridge in a specific gun, then you get to design one that'll work. If you want to have a cartridge that suits some other purpose and you'll figure out the gun later, that's fine too. Remember that it's up to you what you pick. Everything is open. There are no limits. The only limit you might have to consider is when you go to do research. At the research point, you're going to not only look for the cartridges that already exist that might be similar to what you're doing, you're also going to be looking at what brass is available to me. What cartridges exist that I might be able to form more easily or close to what I'm doing to save myself some time and some effort. When it comes to research, I can't emphasize enough. Research, 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 over and over again. Not only does it allow you to pick your brass and that sort of thing, it's going to enhance every aspect of the wildcatting process. If you know everything that's out there and what you're comparing to, it's going to make it easier for you to design. It's going to make it easier for you to come up with a good design that's worth messing with and that'll interest other people, which is really part of the fun of doing this. The next thing you're going to look at is designing your cartridge on paper. When you go to draw the cartridge, it doesn't matter what method you pick. What matters is that you get the correct dimensions down on paper. So you're going to use your research to put your base dimension down. You need to set a shoulder dimension, set your lengths, neck dimensions, whatever those might be. Just make sure that you pick the correct numbers because you're going to use those to make your tools. Now, once you have a good drawing, you're going to go back and compare your cartridge to the existing things in the world. You've already done some research, so you probably have a pretty good idea. But what you want to do is, you probably don't want to repeat what other people have done simply because there's not very much excitement in putting your name on work that somebody else already did. And it's a little embarrassing to go to the range if you don't realize that you've done that and have somebody call you on the carpet for designing somebody else's work. So once you've compared cartridges and you know that you have a unique design, then we're going to start talking about making reamers. If you choose to make a 1-flute reamer versus a 2-flute reamer, just think about the time and effort that's involved for the tool you're making.
If it's a large diameter cartridge, you'll probably want a 2-flute to help avoid warpage and to help avoid the tool grabbing when you're making your die or if you're chambering a barrel. The next consideration with your reamer is whether or not you're going to put the neck on it. If you put the neck on, just keep in mind you have to hold all those dimensions and you're going to have to do all that relief grinding. If you leave it off, then you take care of that in the resizing die itself by reaming the pilot hole to the correct dimension. When milling the relief cut, just remember about center line. You want to stay on center line with the reamer and never move the cutting edge above or below that. Stay plus or minus 10 thousandths. That'll keep you in line. When you do your relief grinding, remember that the only two things that touch are the pilot and the cutting edge. Relieve everything else and you'll be fine. And when you go to do the final sharpening, that's a hand process. It's gentle, take a little time, look real close. If you need to use magnifying glasses, that's the way to do it. Slow down and do a good job and it'll cut amazingly well for you. When it comes to heat treating, remember, don't wiggle when you dip. Save that for the dance floor. And the other thing is, don't touch the bottom of the can, but I don't think I'll go there. When it comes to reaming, just remember basic rules. If the machine sounds wrong, slow down, slow the machine down, use more cutting oil, watch the size of the chips, all those basic things. When you make a strategy for forming brass, remain flexible. When you get to the next project, it's probably not going to work the same way. You're going to have to come up with a new strategy and find out what works with that particular design. Now, read the brass, read the brass, read the brass is going to be your solution when it comes to this flexibility. Practice on your own projects first. If you try to take on a project for somebody else for your first project, the pressure will be immense. Don't do that. Practice on your own projects and have a little bit of fun, because that's what it's all about. Take a step back if you run into a problem. Don't force yourself to try and solve the problem right there on the spot. Call somebody else who's had some experience with it, or possibly just take the night off, relax, and come back to it the next morning. Oftentimes these problems almost solve themselves if you just step back for a minute. Nothing beats experience. If you don't get this practice in, you're going to have problems. Now, I'd like to thank you for taking this course. It's been a lot of fun for me. I hope you enjoy it, and I hope that you'll be out there building Wildcats. I know I will be.